This episode of Science Max is all about earthquakes.
Exciting.
How do we build something that won't fall apart when shaken? Plus a lot of other ways to shake things or build things.
Science!
All on this episode of Science Max Experiments at Large.
Greetings, Science Maximites. My name is Phil, and this is Science Max Experiments at Large. Today, we're going to be looking at earthquakes. Earthquakes! Huh. Today, we're going to be looking at how to build something. That was supposed to happen earlier. Today, we're going to be looking at how to build something that stands up to the shaking of an earthquake. Earthquakes happen when two plates on the Earth's surface rub together, and it causes the ground to shake. It causes the ground to shake. Sometimes it shakes a little, sometimes it shakes a lot. Chances are you do not live in a place that has earthquakes. But if you do, ask an adult what to do during an earthquake so you can be safe. Modern buildings that are built in earthquake zones are designed to withstand the shaking. But how do scientists and engineers build a building that stands up to the shaking of an earthquake? Well, that's what we're going to be looking at today. First thing we have to do is simulate an earthquake. We're going to build a shaker table. And here's what you need. 2 books and... Two books, 4 elastic bands, and four rubber balls. Oh, wait. Okay. Four rubber balls. All right, so the first thing you do is actually take your 4 elastic bands and wrap them around your books. Put one set on one side, one set on the other side, till you have that. Then you take your 4 balls and you stick them in between the books in the middle-ish area. But you don't want to have them too close to the edges. And now 2 at the back. And ta-da! You've made your own shaker table. What are you shaking, you ask? I will show you. You build a tower. Like this one here that I built out of building blocks. So here's what you do.
You'll need your base to be securely attached to the shaker table. I use painter's tape because it'll come off again without harming the books.
And what I want to find out is just how much shaking this tower can take before it falls apart. Ready? Oh. And there it goes. And when you've done that, what you do is you be a Science Maximite and you design another tower. And you tape it down to your shaker table and see if you can make this tower fall down in an earthquake. And if you built it really well, probably won't. But you don't have to just use building blocks. There's all kinds of other materials you can use. Check out this building, which is really tall, and you'll see there's a cup at the top, and that's for a baseball. Put it up at the top, and that means there's a weight up there. And then we shake it, and we see what happens. Oh no! Oh, there it goes. So that is what we're going to be doing today on Science Max Experiments at Large. We're going to be making a giant shaker table and putting a giant structure on top and seeing how we design it to make sure it stands up to the shaking of an earthquake. I'm going to need an expert to help me, though. Oh, I know. Anne would be really good at this. Okay, all I need to do is get Anne, and we can start. Oh, come on. There it is. All right.
Hey, Anne, I feel weird. Why do I feel weird?
I think you're a chair.
Well, that's not good. Hold on a second.
Am I good? Okay. Hi, Anne. Good to see you. Here's your lab coat.
Thank you.
So you're from Let's Talk Science, right?
I am.
All about science education, just like us. Today, I need your help to max out our earthquake table. This is the table
This looks
part,
great.
obviously, but this is a tower I've made out of popsicle sticks. So in order to max it out, I've already built a large shaker table. Come on. This is my large shaker table. So it's got basketballs underneath as the 4 balls, but it works exactly the same. Whoa. Okay, so what kind of tower should we make for the shaker table?
If we want something tall, then we'll reinforce it a couple spots. But the true test, it's gotta have some sort of weight on top so that it will mimic the weight that would be on a real tower.
Right, so maybe I could get a plastic bin and I'll just put some sandbags for weight inside.
That would be perfect.
And then balls, so that when it falls over, the balls will go everywhere.
That would be perfect.
Okay, great. Shake off. I don't know. I think we should just get off.
Another thing that happens during an earthquake is soil liquefaction. Liquefaction means something turns to liquid. In this case, the very ground you might be standing on. Here's how you can experiment with soil liquefaction. All you need is a plastic container and some water, not very much, barely enough to cover the bottom of the container, because what you're gonna put in next is sand. And you wanna put it in there and spread it around. Just add enough sand so it just starts to turn dry on the very last layer. So here is a house that I'm going to put on top. And now I will simulate an earthquake. The water rises up and it sort of turns to liquid. Soil liquefaction. And heavy things like houses and cars, they tend to sink like that. And then the soil rehardens and everybody's houses are stuck in the mud. Now, let's max it out. This is a giant tub of sand and water, and this is a vibrating platform that will simulate an earthquake. Now, as you can see, this sand is totally solid. I can jump all around on this sand, no problem. But when I turn on the vibrating table and simulate an earthquake, things will change. The vibrations bring the water below the sand to the surface and cause the sand particles to separate. What was solid now turns to liquid in my simulated earthquake, and I start to sink. I'm up to my shins! And there you go, soil liquefaction. Hey, look at that. It's totally solid. Woo-hoo-hoo! Soil liquefaction! I'm totally... Uh-oh. You know what I realized? When it stops vibrating, it really becomes solid again, and it's very tough to... Well, there you go. Soil liquefaction. I'm really kind of stuck in here. So Ann and I have made a large shaker table. Now it's just a matter of designing a building. We use lumber and cut it up, use screws to attach it all together, put a platform on top for a weight, and attach it securely to our shaker table. The building is super simple, just 4 corners and a few planks around the outside. No structure in the middle. And finally, the big heavy weight on the top. There. We attach a pole to the shaker table so we can shake from a safe distance and try it out. Okay, very slow.
Forward.
Let's see how much shaking it can stand with our shakeometer.
That seems to be okay.
Just kidding.
Oh no. Oh no! We barely start to shake our tower before it collapses. Oh, that didn't really last very long, did it? It completely folded up on itself. What do we do to fix this, make it better?
I think the easiest thing we can do is to use thicker wood. It'll make it less wobbly.
Okay, sure, let's make another one. High fives. We do have lots of wood, that's a good thing. Ann and I are trying small improvements every time. There. Our last building used thinner pieces of wood. Now we're using thicker wood, which we think will help keep the weight at the top from collapsing the building. Everything else about the design of our building is the same. We put the weight on top and fix our pole, and we're good to go. All right, you ready? No problem.
Okay. Starting to creak.
But it recovers. You can see it lean, and then it comes back, and it resets.
Definitely doing better than the last one.
Oh, no. I'm impressed.
Uh-oh,
here we go.
But it definitely did better than the first one.
It did better than the first one.
And the thicker wood definitely helped.
But it was really starting to turn.
I think on the next one, we need some platforms in the center to help strengthen it even more.
Earthquake Building 3.0.
Thicker wood this time, but with platforms in the middle.
So we're gonna see how well this version works with these middle parts that'll hopefully reinforce.
And they're just like the floors of a building.
Okay, well, let's find out if it's gonna make any difference.
Starting to wobble a little, but it looks pretty good.
As soon as we start shaking, it's really obvious this building is more solid.
Uh-oh, starting to creak. Oh, it's really starting to creak.
The platforms in the middle really seem to improve the structure. You can see it bend all the way over and still recover. But still, it wasn't long before...
Really starting to lean.
Wow, the extra pieces really kind of made it more impressive.
It definitely lasted a lot longer than the other two.
It did, but here's what I'm wondering. Are we going in the wrong direction?
What do you mean?
Well, because if it's really solid, it resists the change.
Okay, I see where you're going with this.
So if we make it flexible, it can resist the shaking of an earthquake.
I think it's worth a shot.
Yeah, okay, let's do it.
Being a chef is my absolute passion. And cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello. Welcome to Cooking with Science. I'm Buster Beaker. My tuna fish and meatball sub soup is coming along quite nicely. But what will we have for dessert? I know. How about earthquake buildings? Ha ha! It's a building made out of wafer cookies. But the people on Vanilla Street built in the gelatin neighborhood. And the people on Chocolate Street built in the crispy rice part of town. Exciting. Now, here comes the earthquake. Oh no! Oh, it's shaking! Oh, the shaking is come and gone for the people on Chocolate Avenue, and their building is still standing. Now, let's take a look over here on Vanilla Street, and here comes an earthquake. Oh no! Oh dear! Looks like the people on Vanilla Street are going to have to rebuild their building because it's all fallen over and being eaten. Delicious. Buildings can be built the same way, but the kind of soil they sit on make a large difference if there's an earthquake. Shaky, wiggly soil or solid, non-moving soil. So there you go, an experiment you can try at home. Delicious. Well, I'm Buster Beaker, and thank you for joining me on this episode of Cooking with Science. Now to try my soup.
Seismometer in 60 seconds!
Learning how to predict and measure earthquakes is an important branch of science. The Earth is shaking, but which way did the earthquake come from? It's all about measuring the vibrations, and to do that, you need a seismometer. All you need is a ball, some paper cups, some modeling clay, a pencil, and science tape, which is the same thing as invisible tape, except I use this tape for science. First, take your pencil and stick it straight down into the modeling clay. Then, you take your cups and you arrange them in a circle and tape the cups down. And that goes right in the middle, just like that. Now what you do is you take the ball and you carefully balance it on the pencil. Now you have created a seismometer. It will tell you what direction an earthquake came from. Watch, I will be the earthquake. Ready? Did you see that? The ball fell into the cup facing the direction that I hit the table. And now I'm gonna hit the table from over here. Yep, it fell in the direction that I hit the table. Okay, let's try from over here. There you go, your very own seismometer that you can use to measure earthquakes that you create on the table.
Back to our earthquake building. Ann and I tried a few different designs, and they each got a little better. But now we're wondering what would happen if we built the tower out of very flexible material. We used some plastic tubing and attached the wood with bungee cords, which are like big elastics.
Wow, okay, so looks good.
So let's test it.
Okay.
And sure enough, when we start shaking it, the tower holds up to as much shaking as we can give it.
Wait,
What?
aren't we missing something?
Oh. Yeah, we're missing the weight at the top. Of course.
So I think we need to try it again.
So we add the weight to the top, and then everything changes.
Oh, no.
Look at it twist.
Oh, dear.
It's twisted. It's
A
gonna
flexible tower is great until you try to put a weight at the top. And then it just seems really unstable.
go.
Whoa, look at that. It's totally bent.
It didn't break at all, it just fell over.
Yeah, it couldn't even support the weight.
So it was almost too flexible.
So I guess we should go back to a more rigid design. But what if we change the shape a little bit? 'Cause you know what I was thinking? This is a very stable shape. Triangle, because triangles are really strong. What about we make an X?
Like a triangle within a triangle.
Triangle, and then triangle. So that really reinforces all of the shaking, like all of the motion.
We'll never know until we try.
All right. Uh-oh, I have all my friends coming over and I don't have a table. But that's okay. I will make a table using my friends. This is an awesome experiment you can do with 4 friends. Come on in, science friends. I've got Sam and Dylan and Polly here to help me. So everybody turn to your left and sit sideways on the chair and then scooch the chairs into the middle. And then everybody leans back onto the knees of the other person. And then this is why I said you need 4 friends, because you need the 5th person to remove the chairs. Whoa. The reason why this works is because everybody's weight is being supported on the legs of the person next to them. Okay, we're gonna rotate in a circle, everybody. Okay, ready? Here we go, rotating, rotating. Oh, science table. Ooh, hey, we're pretty good at this. Okay, uh-oh. Oh no, oh no! So there you go. Awesome way to make a table using your friends. Well done, science. Here's an experiment you can do to impress the adults in your house. You need 3 glasses, all of equal height, and 3 knives, not sharp knives, the dull knives you use, maybe the ones you use at dinner time. Take your 3 knives and put them in a triangle, all equally spaced out. Then move the knives together to make a little triangle, right like that. Then what you want to do is you want to carefully arrange the knives so each knife is going above one knife and below another knife. So there we go. Then you want to take this careful pattern that you created and you want to put it on top of your 3 glasses. One where each handle of the knives are going to be. And if you place it carefully and you've done the over-unders correctly, it will stay up. Pretty amazing. The knives support their own weight. But they don't just support their own weight, they can support a lot more weight too. Pretty amazing, right? This is a great experiment. It's also something really interesting that we can max out. Come on. And here you go, the maxed out knife balance. I've got 3 pieces of lumber and 3 barrels, and as you can see, the pattern is exactly the same. Under, over, under, over, under, over. Ha-ha. So, the question is, how much faith do I have in science? It totally supports my weight. I know it's going to work because I know that a 2x4, which is the kind of lumber I'm using, can hold up my weight. So that means the structure can support me. Science! You know what the cool thing is? The cool thing is that even though it's holding me up, each one of these pieces of wood is only up because it's supported by the others. You pull one out and it all falls apart.
Ann and I have tried solid towers and flexible towers, and nothing has worked fantastically yet with a big weight on the top. Having a big weight on the top of our tower means we need something that will resist the movement of that weight. So now we're going to start with a triangle. Unlike a rectangle, triangles are very stable. A wider base keeps the structure from swaying too much. And cross braces in the middle mean that there are other triangles within our triangle, all the better to resist movement.
Thank you.
After Ann and I built our tower, we added the weight to the top, secured it to the base, and tried it out.
Okay, here we go.
Looking good.
No problem.
It's not twisting.
It's
Not leaning.
not even creaking.
No, it looks really good.
Wow, this one is really solid.
As you can see, this tower is way more solid than our square tower or the flexible tower.
Okay, look at that. Like, if that's not an earthquake, I don't know what is. Look at that. Look at the way the ground is moving.
I don't know if we can shake it much more than this.
Faster.
Our triangular tower is up past a level of shaking that made the other towers collapse. Now it's time to max out the shaking.
There's only one level of shaking that we can do above this.
What's that?
We shake from either side.
We give it all we have. The floor was bouncing from side to side, the tower was tilting, and was totally solid.
It's still holding strong.
In fact, Anne and I wore out before the building showed any signs of falling over.
I think we've done it.
Woo! Nice job.
Nice. Science Max experiments at large earthquake-proof building. I mean, come on. That was impressive.
I like it.
Science Max! Today on Science Max, we're using the forces.
Pendulums are pretty simple. It swings back and forth.
Marbles, dominoes, sledgehammer, trebuchet, rockets, levers, rockets, tension, and that's just the main experiment.
Maxed out dominoes.
I love that idea.
All this and more on this episode of Science Max Experiments at Large.
Greetings, Science Maximites. My name is Phil, and welcome to Science Max Experiments at Large. Today, we're going to be looking at air pressure and friction and simple machines like levers, pulleys, and gears. We're going to look at some rotational energy, some spring tension, and gravity. We need all those things because we're building Rube Goldberg machines. Rube Goldberg machines. Rube Goldberg machines. Rube Goldberg machines. Rube Goldberg. You heard me say Rube Goldberg machine. Okay, we got that part. Okay, good. Rube Goldberg was a cartoonist who came up with the idea of having a simple task done by a machine that was extremely complicated. There are Rube Goldberg competitions all over the world, and there's only a few rules. First, a human can only touch it once by starting the whole thing off, and then the machine has to work all on its own. I know what you're thinking. You're thinking, Phil, what's the science behind a Rube Goldberg machine? Well, it's all about changing energy. Remember, you start the whole thing off with just a little push. But if you want the machine to keep going and going and going, you have to come up with clever ways to add more energy to the system so you've got more energy to keep the machine going. So check this out. A bunch of stacked dominoes, which will start a chain reaction that leads to this mouse trap, which has all of its energy stored in the spring tension, which will release the ball. Boing! Check this one out. It's a bunch of pulleys, and there's a rope that goes up and down and up, attached to this lever where there's a ball, and there's a big heavy weight here. And when the weight gets knocked off the table, the ball falls into the hole and then goes down the tube, and so on. Check this one out. Here's a great way to change the direction of something. Say the ball falls on this lever. Well, it's weighted on this end, but then the weight falls off and the ball goes this way. And, the portal turned on. I gotta pick an expert. Okay, hold on a second. 10 seconds before the portal resets. Sonia from the Ontario Science Center. Perfect. And there we go. Tons of time. 3, 2, 1. Sonia!
Hey.
I portaled in 3 blocks away. I had to run here.
Okay. You're here now?
Yeah, I didn't put the coordinates in when I left. Anyway.
It's okay. Breathe.
Sonia from the Ontario Science Center. I'm glad you're here
Nice.
because we are gonna build a Rube Goldberg machine.
Really?
Yeah.
Oh my gosh, I'm so excited.
Yeah?
Yes.
I'm excited too. Check it out. This giant room. I've never done anything with it, so why don't we build a giant machine in here?
Why
right?
not?
Okay, so here's the rules. The Rube Goldberg machine has to start with one simple thing, right?
Yep.
So we're gonna start with this marble, and we send it on its way, and then a whole bunch of stuff happens, and at the end, we press that button.
That button?
Yeah.
What does it do?
I've never used it before, but when we hit that button, we get cake.
Cake?
A cake will portal in and we'll have cake.
Oh my goodness, can we get chocolate cake?
We can totally have chocolate cake.
All right, now I'm really, really excited.
Okay, so can I start?
Absolutely.
Great, because I saw some stuff over here.
Okay.
This is a pendulum. It's a weight that swings. It swings back and forth. Pendulums are pretty simple. It swings back and forth. Predicting the path of a pendulum,
Pretty simple. It's gonna swing back and forth. But wait! As I make it so much more complex by adding a pendulum. Now I've got a pendulum down here, and that one swings back and forth, and I've got a pendulum up here that swings back and forth. What will happen to this part of the pendulum when I let it go? Can you predict? Let's find out. This is a double pendulum, and predicting the path of a double pendulum is really difficult. It's still simple physics, but because there's a moving part attached to a moving part, it makes it way more complex. So, the question is, can we max it out even more? Of course we can. These are chaos pendulums. This one's a lever, and it's got another lever on the end. Whoa, and this one here is a perfectly balanced lever, and it's got a pendulum on either side. Whoa. Scientists and engineers have always said that the more moving parts something has, the more complex they are. Science. Sonia and I are taking turns building our Rube Goldberg machine. The first section was my turn, and I explained it to Sonia. Right here, we have what is known as a ramp. Ooh, yeah, I know you know.
Fancy.
Right, so we put a marble on the ramp that rolls along this thing into what is known as a pylon. And then we've got these guys right here, which are dominoes. And when that falls off the table, it'll pull on the string, and then it's attached to this. Now, this is the release mechanism, so when that string gets pulled, it will let go, and it will fire this, which is a trebuchet.
All right, should we test it out?
Absolutely. You
Can
want
I
to try
try
it?
it?
Please.
Yeah.
Okay.
Okay, 3, 2, 1. Huh.
Wait.
Didn't go. Why didn't?
Well, the domino doesn't seem to be heavy enough to make this contraption fire.
You know what, Phil?
What?
I have an idea.
Oh, yeah?
Maxed out dominoes.
Maxed out dominoes. I love that idea. Why are they maxed out? Do they glow in the dark?
We'll see.
Do they produce electricity?
We'll see.
Do they talk to animals?
We will see.
Do they dissolve in water? Whoa, maxed out dominoes.
That's what I'm talking about.
These are very maxed out. Okay, so
we
now.
started off with this domino. Then we went bigger.
Yeah.
Bigger,
Yeah.
bigger. And we went to the biggest.
Right.
And this is where we're gonna get the most weight, which is gonna trigger it and release.
Ha ha! Woohoo! Here we go. 3, 2, 1.
Here we go.
The one thing to remember about Rube Goldberg machines is they never work perfectly every time.
Didn't go.
But we tweaked it and adjusted things, and then.
Here we go.
3, 2, 1. Whoa!
Nice. That was pretty far.
Yeah, check this out. Whoa. Okay, so
Nice.
now that we've got the trebuchet firing, and the ball is going over there, we need to get the ball going over here
Yeah.
to
The
cake button.
cake button.
I can't wait for the cake. So I have an idea. Come on.
Okay.
No, wait. Changing direction stuff is over.
Okay.
Now we're gonna talk about tension. What's tension? One more than nine-shin. Get it? Because tension and that's, okay, tension is the force that we usually talk about when we think about pulling a rope or a chain or something like that, because you know the old expression, you can't push a rope. But today we are gonna push a rope. I have a rope right here, and I'm going to push it using another force called flexion. I've got some pieces of plastic here, and they bend or flex. And when they do, they want to spring back. But I'm gonna prevent them from springing back by putting them in between these nuts. And look, the rope now stays up. I take another piece, and I stick it on this knot, and then I bend it all the way. This is not terrifying. Really, it's not terrifying at all. Okay, good. And then I take this piece, and I put it here, and I bend it around, and so now we have a rope that's being pushed, and we're defying gravity, and we're making a cool art sculpture. All right, one more here. Ooh, okay, here we go. And flexing. And, whoa. Ha-ha! There you go. I've pushed a rope, defied gravity, and made a cool art sculpture. Okay, well, I guess technically I haven't really pushed the rope because we're still pulling from each knot. And I guess I haven't really defied gravity because that one's sitting on the table and all the others are sitting on top of that. But you can't argue that I made a cool art sculpture. Ha-ha! Art! I mean, science. Sonia and I are maxing out a Rube Goldberg machine. Whoa! The first part worked pretty well, and now we need to change the ball's direction. This is a trebuchet. Trebuchet fires the ball, right?
Yeah.
Right now I want to tell you the story of the ball. First, it goes through this fancy film of tin foil.
Aluminum foil?
Right, aluminum foil, because it's, yeah, you're right, it's made of aluminum. It enters this large receptacle.
A garbage can?
You also could be called a garbage can. It falls into this conular device.
Funnel?
A funnel, yes, you could call it a funnel. And then it enters the change-o-direction-o-matic, which is a lever. There's a weight on that end, then it falls off, then the ball goes this way.
Phil?
Or that way. The one thing you need most of all when making a Rube Goldberg machine is patience. Ball goes in the funnel, knocks that off, changes direction, and then it goes this way.
Okay.
And that's all I got so far.
So, not bad.
Yeah.
But we really want to get closer to that way.
Right, because that's the button that gives us cake.
How about we use some chemical energy for this?
Ooh, chemical energy.
I have an idea for this one. Let me go get it.
Go for it.
This is my idea.
Okay.
Ball's actually gonna roll down the tube.
Oh yeah, because this is a rat trap, right?
Yeah.
Which is like bigger than a mouse trap.
And then it's gonna hit it. Yeah. Nice.
Ooh, so this flips around.
Exactly.
And what's this?
That is something called an antacid tablet. Some water.
And the antacid and the water react. Oh!
It blew. Do you want to test it out?
Sure, can I?
Okay.
Okay, ball comes through this, goes down there, comes out of this, and on the ramp.
Onto the trap.
Oh.
And
Ah! So then
Nice.
it fires up
Yep.
and hits something else
Yeah.
and something button cake. So we got a lot of different energies, but you know what one we're missing?
What?
Is electrical energy.
yeah, you're actually right.
I've got a great idea. Hold on.
All right. Let's see what he comes up with.
This is a chain of beads, and this is glass. Now, if I was to drop the chain of beads, what will happen? It will fall. Yes, that's right. It'll fall because of gravity. But watch this. This side goes up. Why? Because of gravity. Wait a minute. Why does one side go up because of gravity? Well, it gets a little complicated, but I can explain. But I think I'll have to put the beads back in the glass. Okay, so what's going on? Well, when this part of the chain starts falling out, it gets longer and longer, and it has more mass than this side of the chain. And if it has more mass, then it has more inertia. And when it starts yanking out very hard, this side of the chain gets yanked up out of the glass very quickly. When it gets yanked up hard, it flies into the air. But then, of course, the direction has to change, so it goes around a curve and then goes back down. Because of the speed that it's going, that curve starts lifting up over the top of the glass. And that's how it works. There's a big difference in energy because this chain falls far. I try it from here, and it doesn't work as well. Why? Because the drop from here to here isn't as big. You want lots of force acting on the falling chain, which means the higher you do it from, the better it works. So maybe we should max it out. Yeah. But wait, we should wait for it to stop. And now let's max it out. This is a really long chain, and this is a really long drop. Let's see what happens. Whoa! Look at that. Whoa, super maxed out! Science! Sonia and I have used potential energy, the lever, and chemical energy. But you know what one we're missing?
What?
Is electrical energy. Electromagnetism. So watch. The chemical rockets, which we've had from before, they'll fire up, they'll hit the underside of this tray. The marbles will fall, and flick this switch. See that sledgehammer?
Uh-huh.
This is an electromagnet, and it will attract the metal in the sledgehammer. Watch this, ready?
There.
There. Magnetized, electromagnetism. Now, when the marbles fall, it'll turn the electromagnet off, and the hammer will fall.
Oh, that's pretty cool, actually.
Right?
Can we
So
try it?
let's try it. Here's something we didn't know. Predicting the flight path of an antacid rocket canister is almost impossible. We had them aim the same way every time. But we stuck with it, and being patient is key, and eventually it worked. The chemical rockets fire, and they hit the tray. All right!
That's pretty cool.
Yeah, so now we just need hammer hit something, and then something, 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 button, cake.
I have an idea.
All right. Cake any minute now. This is a basketball. It bounces. This is a golf ball. It bounces. But it never bounces as high as where I dropped it from. But watch as I put the golf ball on top of the basketball. Whoa! Why does the golf ball bounce higher than where I dropped it from? How is this possible? I only bounced the golf ball from 1 meter high. So what's going on? Well, as the basketball hits the ground, it compresses, storing the potential energy of its bounce, about to give that energy back as it bounces up again. But this energy works as a springboard for the golf ball. And since the golf ball has a lot less mass than the basketball, the upwards kinetic energy of the basketball is given to the golf ball. So, let's max it out. Ball, on a ball, on a ball. 3-ball bounce. Oh, did you see that? Ball, on a ball, on a ball, on a ball. Quadruple ball bounce. Oh, oh. Oh. No, wait. Turns out getting 4 balls to drop straight down on top of each other is pretty difficult. So, we know the mass of the ball is important. Why don't we max it out in a different way? This is a Swiss ball for exercising. It has a lot more mass than a golf ball. So, let's try it out. There you go. The transfer of energy between balls. A great way to lose golf balls. Sonia has added one more step to our Rube Goldberg machine, a Stomp rocket. It's a hammer rocket.
Exactly.
I like
so
that.
what's gonna happen is the hammer is gonna hit our bottle, which is gonna release all that air that's built up inside of it. It's gonna hit that button.
Wait. The rocket hits the button.
And then we get some
Cake!
cake.
Oh, so this is it. So we're done the Rube Goldberg machine with this last step.
Okay.
Do you want to do it?
I think we should do it.
Ready?
Ready?
3, 2, 1. Oh. Let's pause here just before the cake portal's in and recap the science. A marble on top of this ramp has potential energy. As it rolls down, that changes to kinetic energy, which transfers to some stacked dominoes. They fall in a chain reaction, finally causing bigger and bigger dominoes to fall, giving the last domino enough mass to pull a string, attached through some pulleys, to a quick release on a trebuchet. Now, a trebuchet is a first-class lever, with a weight on one side and a sling and a ball on the other. If the weight falls, the sling releases the ball at the right moment and it sails through the air. It's caught in a garbage can and changes directions on a few ramps and another lever as a teeter-totter. Finally, it falls onto a rat trap which has more energy stored in the tension of the spring. The rat trap smacks another lever, which flips around, turning over some antacid rockets. This allows the antacid to mix with the water and start a chemical reaction that produces carbon dioxide, which eventually builds up enough pressure to fire the container to another lever, which tips, dropping some marbles on a string attached to a switch. That turns off the electricity to our electromagnet. And when an electromagnet doesn't have electricity, it stops being a magnet. So our sledgehammer starts to fall. Now, our sledgehammer is heavy, so it has both mass and speed when it hits this plastic bottle. All that inertia crushes the bottle, reducing its volume. The air gets put under pressure and pushes out through a tube, which takes our Stomp rocket with it. The Stomp rocket flies through the air and hits our cake button, which then portals in some cake.
Guess we really didn't think that through, huh? The cake should have landed on a table or something.
Table would have been nice.
There you go, Science Max Experiments at Large, Rube Goldberg machine. Are you sure you don't want some of this cake?
No, let's
But,
let's go.
Science Max! Newton's third law is the science behind balloon-powered rocket cars. It's also the science behind a maxed-out rocket car that I can ride. Plus bowling balls and an interrupting sign. Today on Science Max, Experiments at Large. Greetings, Science Maximites. I am Phil McCordick, and this is Science Max Experiments at Large. Today, we're going to be experimenting with the balloon-powered car. Here's how it works. Woohoo! It all has to do with Newton's third law.
Newton's third law. For every action, there is an equal and opposite reaction.
We don't have to do this now. This is all for later. We can build the cars first, and then we can, let's go over here. So how do you build a balloon-powered car? Well, I suggest you be Science Maximites, because there's any number of ways you can build a balloon-powered car. You do not have to follow my design. You should come up with one of your own. It may even be better than the one I built. But I will give you some tips, though, that make it a lot easier. First of all, you need something to stick your balloon on that has an opening on it. I used a turkey baster for this car. I just pop the top off, and remember to tell an adult that you're using the turkey baster. And then you stick the balloon on there, and it allows you to attach something to the car, and it also makes it easier to blow up the balloon. You can use any number of things, even just any kind of tube that you find lying around. It helps you attach the balloon to the car, and it helps you blow up the balloon way easier. The other thing you should think about when you make your balloon-powered car is how you're going to make the wheels roll. Once you've decided on the base of the car, you could use anything, even just a piece of cardboard like this. You can do your wheels in two ways. The first way is to attach the wheels to the axle. This is how I made the axle of this car. I used a shish kebab skewer, and I stuck it inside a straw, just like that. And then I attached the lids to the shish kebab skewer. So the lids and the shish kebab skewer are attached, and they rotate in the straw. That's one way to make the wheels turn. The other way is to tape down the axle or whatever you're going to use and have the wheels spin around on the axle. Two great ways to make your wheels turn, and it really kind of depends on the wheels you're using. You can make your own design and keep refining it and making it better and faster, or do what I like to do and make a whole bunch of different cars. So we've got this one. This one I made out of paper plates, and this is a snorkel. Awesome. This one is the rock car, because there's a rock on it. I've got the Dragster model. It's a long broom handle, and it might not work that well, but who knows? And this is my favorite design. It's made out of waffles and an ice cube tray. This is why I make a whole bunch of different cars, because I can race them.
Sunday at the Science Maxodrome. It's the balloon-powered car winner-take-all drag race of awesome.
First up, the Eliminator. Woohoo!
Better late than never, it's the Procrastinator. crushing the competition. It's the Terminator. Feel the chill of the refrigerator.
All right!
And last but not least, the, regurgitator.
Well, when you build your balloon-powered cars, you can figure out what worked or what didn't work and try modifying your designs to make them work even better. That is science. And now we're gonna max it out, because this is Science Max Experiments at Large. So we're gonna take that small balloon-powered car that we just built and we're gonna make it much, much bigger. I'm gonna go to the Center for Skills Development and Training, and we're gonna use the science behind this small balloon-powered car, and we're gonna make it big. That science is Newton's third law. But there's plenty of
third law.
No, there's,
For every action,
there's
there is
plenty
an
of time
equal
for this
and
later. We're not
opposite
doing
reaction.
we're not doing this bit now. We're doing that bit in a minute. So we could no, I said we're doing it later. We're doing it later. Here. Whoa. Hi, Sarah.
Hi, Phil.
This is Sarah, and she's got a master's degree in physics from McMaster University.
That's right.
And we're gonna be talking about Newton's third law. Oh, look out, duck! Sorry. There was a sign that kept coming in. Never mind. Newton's third law. Well, what is that?
For every action, there's an equal and opposite reaction.
Right, so how does that work with our balloon car?
Ah, cool. Okay, so if you blow up the balloon, what's gonna happen when you release it is the air is gonna push out with a certain force, which in turn is gonna cause the cart to move forward with the exact same force.
Yeah, works great. So how come it doesn't work with my rock cart?
Ah, wow. Well, actually, it did work. So the balloon still pushes with the exact same force, which causes the cart to have the exact same force push forward, but your rock is really heavy, so you probably didn't see it move.
Oh, so a lighter cart works better with the same amount of force.
That's it.
Well, there you go. Newton's third law. What?
Newton's third law. For every action, there is an equal and opposite reaction.
I'm really starting to dislike that sign.
Phil, are you okay?
Yeah, I'm fine.
Our small balloon-powered car works because of Newton's third law. For every action, there's an equal and opposite reaction. The air pushing out the balloon this way pushes the car with the same amount of force this way. So, in order to max it out, the plan is just to get a bigger wheeled cart and a much bigger balloon. So, everything should work out the same.
Okay, so sorry. Oh, I thought what we would do is in order to max out the balloon-powered car, what we need is a cart to start with, and then I ride it. And we have a giant balloon, and then I go.
Do you have a giant balloon?
Ha 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 ha! Giant balloon! So, step one, Sarah blows up the balloon.
Okay.
Wait. Use this air compressor, it'll probably be a lot faster.
Sarah and I get to work blowing up the balloon, and it takes a long time. A very long time.
Okay, human-sized balloon-powered car test. Take one. All right, Sarah.
You got it?
Yeah. Okay, let it go.
Okay, go!
Let it go.
You did.
You did let it go.
I had to let go.
Nothing is happening.
It's not coming out fast enough, and you're a bit too massive. I don't think it's gonna work like this.
Really?
Yeah.
Okay. Balloon-powered car test 2. No fill. I'll just take it. What happened?
I don't think it worked. The balloon popped. Phil, are you okay?
This is why you wear protective eyewear. Yeah. So, that didn't work.
No.
No. Should we get another balloon?
I think we need something else.
Okay, well, the air coming out of the balloon just didn't have enough force, so.
We need the air to come out with more force.
Yeah, do we get, what, a bigger balloon?
I don't think that's gonna work. I don't think it's that. I think we need something with compressed air.
Oh, like a scuba tank or a...
Fire extinguisher, something like that. Yeah, that's what we need.
Okay, sure. Well, we can, all right, so I don't know if that's safe to do that, so we'd have to build like a cage or
Yeah,
something?
I don't know if it's gonna work on this.
All right, well, back to the drawing board. So
Okay.
what we should do is we should get
We need to find these tanks.
get the tanks, and then we make like a frame out of aluminum or something.
Okay, that could work.
Yeah,
That's
they
a
can
good
hold the
idea.
tank, so
Yeah.
they're safe. And then what we should do is...
Who was Isaac Newton? He was a mathematician and probably #1 on the list of top scientists of all time. Albert Einstein said, Isaac Newton was the smartest person that ever lived. You've got to be special if Einstein is calling you smart. Newton's 3 laws of motion was a huge idea, but did you know Newton also came up with the idea of gravity? The famous story is that in 1666, Isaac Newton was sitting under an apple tree when he watched an apple fall and wondered why. Hey everyone, I just invented gravity, which was a big relief because up until then, everyone was just floating around. Okay, so it didn't happen like that. He didn't invent gravity, he gave a name to this invisible force and then described how it works. Not only did it make things fall down, but it was the same force that kept the moon circling the Earth and the Earth circling the sun. And he invented a new kind of math to explain how. We now call it calculus. See? I told you he was smart. He's very smart. This is hydrophobic coating. Hydrophobic literally means afraid of water, but it's not actually afraid of water. The chemistry of a hydrophobic coating prevents water molecules from penetrating anything you spray it on. You can get this stuff at the hardware store, and if you want, be Science Maximites and get an adult and think of the coolest thing you could spray with hydrophobic coating. I like to use things that do not go well when you put them in water, like tissue. Yeah, doesn't look great when it gets wet. Here's a tissue coated in hydrophobic coating. Huh? Weird. Or it works the same with a paper towel. Paper towel in water, paper towel covered in hydrophobic coating, stays dry. Or how about a dinner roll? Dinner rolls really don't like water. See? Gross. But a dinner roll coated in hydrophobic coating? Weird. Just don't eat it. Now, it's time to max it out. I have coated half of my lab coat in hydrophobic coating, and the other half I have not. Hydrophobic coating, regular lab coat. Half of me is wet, and half of me is dry. What's more, half of my outfit ended up being wet and half dry because the lab coat was protecting my outfit from getting wet. Now it's time to max it out even more. We have coated my entire outfit in hydrophobic spray. My shirt, my pants, and my lab coat. The pants have been taped to rubber boots, so no water's getting in there. And my shirt has been taped to my pants, so no water's getting in there. So here's the question. Can I get into the pool and out of the pool and stay dry? Let's find out. In the pool, out of the pool, and I'm still mostly dry. Now here's what really happened. I got into the pool, and I realized I should have duct taped the pocket, because all the water went in there, down into the rubber boots, started filling up the rubber boots, and now my entire leg is full of water because the hydrophobic coating isn't letting it come out. So the hydrophobic coating isn't keeping the water out, now it's keeping the water in.
Let's take a closer look at Newton's third law.
Newton's third law. For every action, there is an equal and opposite reaction.
Okay. All right, let's watch it back.
When the sign hits me, I exert a force on the sign in the opposite direction. That makes the sign stop moving. It also exerts an equal force on me, causing me to fly off in this direction. Now, if I was to push this sign, I'm not only pushing the sign this way, but my feet are pushing against the ground in the opposite direction. It's, Well, it's really easier to see if I'm not standing on the ground. Oh, hold on. Okay, so, Oh, okay. So now that I'm hanging, watch. I push on the sign, but when I exert force on the sign to make it go this way, I go that way. Well, actually, it doesn't work as well because the sign isn't as heavy as I am. So wait, I have this over here. This is a barrel, and it has stuff in it, and it weighs as much as I do. Okay, so watch. If I push on the barrel like that, I go away from it as much as it goes away from me. So, there you have it. Newton's
third.
No, hold on. Newton's
third law.
Newton's third law. Okay, go.
Newton's third law. For every action, there is an equal and opposite reaction.
So, using a giant balloon to push me on a cart didn't work.
What happened?
The plan now is to use the compressed gas cylinder. Just like a balloon, these cylinders contain a lot of air. If we get a cart and put a gas cylinder in a cage for safety on the back and open the valve, the escaping air might have enough force to push me.
This is 2 cubic meters of air. If we were to put it in a balloon, the balloon would be this big. But if we compress the air, we can fit it all into one of these, a steel tank. This is what we're going to be using next for our air-powered car. Got it?
Yep.
All right.
Good.
So Sarah and I have been hard at work, and we've built the air-powered cart. We can't call it a balloon-powered cart anymore because now we've got a compressed air tank, so it's not a balloon that powers it.
Exactly.
Okay, so I'm gonna sit on here, Sarah's gonna turn on the tank, and I'm gonna go. And before we do this, we should say, do not, under any circumstances, try this at home. We are trained professionals. You ready?
I'm ready.
Okay, high five first. Okay, now we do it.
Okay, so before I turn the tank on, make sure your feet are down and the brakes are on.
Gotcha.
Don't take them off till I say go.
You have got it.
All right.
Ready?
Okay.
Yeah!
It worked.
Yeah, it did work, but I feel like it could work better.
You want to go faster?
I do want to go faster. This reminds me of the rock car.
Yeah.
Where we didn't have a big enough balloon.
We need more force.
We need more force. So should we get a bigger tank?
Let's get more tanks.
More?
Tanks, more force. You're gonna go faster forward. Newton's third law.
Newton's third law, high five. All right, let's do it.
All right.
Whoa. This is Newton's cradle, and it's a really cool toy that demonstrates all kinds of laws of motion, including Newton's third law. What you do is you pull this one ball out, and when it hits these balls, they exert force on that ball to make it stop moving, but it exerts force on these balls, which travels through the balls and makes this one on the end fly out, like that. Now, there's a lot going on here, but you can really see how the force is equal that you put in and you get out if you use 2 balls. I swing 2 balls up, and 2 balls go out that side. Isn't that cool? Now, it wouldn't be science max unless we maxed it out, so come on. Whoa, okay. This is one we built out of bowling balls. Bowling balls, bowling balls, instead of smaller balls. And I think it's gonna work the same way. Let's find out. You throw one out, and yeah, it works the same. Okay, now let's try it with 2 balls. Okay, ready? Wait. And 2 balls, throw them out. And 2 balls on that side. All right, so there you have it. Whoa. Newton's third law. Oh.
Newton's third law. For every action, there is an equal and opposite reaction.
So our single pressurized tank created enough force to move me, but not very fast. The plan now is to do 2 things. First, we're going to triple the amount of thrust by using 3 tanks. We're also going to use some pipes that lock into each other to give me an initial push. These pipes slide together, and when the air is turned on, the pressure in the pipes will cause them to slide apart, which will push me forward. After that, I use what's left in the tanks to keep going.
All right, now it's time to max it out. I've enlisted the help of a few more Science Max people. Thank you very much, Corey. You'll see now we have 3 tanks of compressed gas, and we've also got this nifty little contraption. How does this work, Sarah?
All right, so each tank is attached to a tube, and you can see that each tube goes into this one main tube, so when we turn them on, pressure's gonna build up, and we're gonna go forward with more force.
Well, that's great. And Reed is stacking cinder blocks, thanks Reed, up so that will push, the pipe will push against the cinder blocks, and then I'll go that way. All right, well, are you guys ready?
I'm ready.
All right, let's do it. Now, again, I have to say, thank you, Corey, I've got it. This is something you definitely don't want to try at home. We are all trained professionals. We have a physics degree here. We've got TV people that make sure that this is safe. So watch it and enjoy, but please don't try any of this at home. Okay, I'm ready. Sarah, count me down.
3, 2, 1.
Woo! That was awesome!
That was really awesome.
All right, high fives, high fives. Yeah. And it's raining now, so it looks like we're gonna have to stop. So thank you very much for joining us on Science Max Experiments at Large in our episode on Newton's third law. Science Max!
This episode of Science Max Experiments at Large is all about light. And bending light to your will. Right? And challenges me to an ever more tricky game of light manipulation. Plus lasers, periscopes, and what does that have to do with light?
Cut to animation!
Find out on Science Max Experiments at Large.
Greetings, Science Maximites. I'm Phil, and today on Science Max Experiments at Large, we're gonna be looking at light. Okay. Stay. That wasn't supposed to happen. I was supposed to press that button, and there was supposed to be all these lasers and special effects, but it didn't. Well, today on Science Max Experiments at Large, we're not gonna be doing one experiment. We're gonna be doing a number of small experiments because we are going to do a light manipulation challenge. I'm gonna get an expert, and she's going to challenge me to a game of light manipulation because I am the master of light. Oh. Well, at least the green lights are working. And okay, forget it. I'm just gonna turn it back to normal. Come on, back to. I'm gonna work on that later. I'm gonna need an expert to help me though. Oh, I know. Anne would be really good at this. It really does look kind of weird in here, doesn't it? Oh well.
You okay?
Hi.
Hi,
Anne.
Phil.
Yeah, I couldn't see what I was doing. Here's your lab coat.
Oh.
Thank you for coming.
Great.
Now you're from Let's Talk Science, right?
Yes, that's right.
All about science education, just like us. Now you're gonna challenge me to a light manipulation game?
A light manipulation game. I've been working on a series of challenges since last time we talked. Each
Awesome.
a little more difficult than the last.
Well, this is gonna be great, because I am the light manipulation master.
Okay, well, we'll see about that.
Okay.
Challenge number 1.
Take a seat.
Oh, that's easy enough.
I have written something on the back side of this ball.
Okay.
And I'm gonna challenge you to read it.
Okay, well, I'm ready. I might be able to read it from here. Let's see.
All right.
Okay, I see something's written on it, but I can't read what it says.
What if you squint?
It looks like a couple lines, maybe? I can't quite tell.
Any ideas how to solve this challenge, Phil?
And I have to be in this chair?
Well, you can get out of the chair to set up your solution. But
Okay.
when you read what I've written on the ball, you have to be sitting in the chair.
Well, it's light manipulation, right?
Mm-hmm.
So, wait a minute, I've got flashlights in case the power goes out, so maybe I can use a flashlight. Haha, okay, ready? Pew!
Huh. Doesn't seem to make it any easier to read. Yeah, I got nothing.
Do you give up already?
No, of course I don't give up.
I told you these were going to be challenging.
This is nothing. I will figure this out.
I don't know yet.
You're going to have to get creative.
I don't know yet, but I will think of something.
Okay.
Okay, I will be back. Here, hold the flashlight. Not looking, not looking. I'm gonna go this way.
I'm going to wait right here.
Okay. Have you ever wondered why you end up upside down when you look at yourself in a spoon? It's because of light reflection. Light is made of photons. Let's say that these tennis balls bouncing off this wall are photons of light. Now, when the surface is flat, like a mirror, the photons, they bounce in and straight back out again. But when the surface is curved, the photons don't go straight out, they get reflected. So now, this photon is going over there, and if we had photons on this side, they would go... I don't even know where those ones are coming from. Then, okay, so we got photons on this side that are going that way, and photons on that side that are going this way. So the top becomes the bottom, and the bottom becomes the top, and that's why you look upside down when you look at yourself in a spoon. Okay, cut to animation, cut to animation!
A lens works by changing the direction of light too. Lenses are made out of curved pieces of glass. When the photons of light pass through the glass, the curved surface makes their paths change. What was only this big before becomes this big when you see it. Lenses are used in microscopes to see things that are really small, or in telescopes to see things that are very far away. Both times they are making something small appear large. Anne has challenged me to figure out how to see a small object far away, and using a lens is my solution.
Check it out. It's a giant magnifying lens.
And I'm gonna use it to magnify the ball so that I can see it.
Sounds great.
All right.
I set the lens in front of the ball, which Anne has turned so I can't see what's on it. I add a light,
Shine it on the ball so that it's a little bit better illuminated.
and then sit in the chair and ask Anne to move it so it's aligned.
All right, so bring it to your left. Yeah, keep going, keep going. Keep going, right about there. Try bringing it closer to the ball. Okay, wait, that makes it smaller. Bring the lens away from the ball. Ooh, wait. Try a little bit further. Ooh, ho, ho, ho.
You're ready for me to spin the ball around?
Yep.
Okay.
It says 71.
Nicely done.
Easy. Solved.
Wait.
What?
That was just the warm-up.
Oh, yeah?
Yep. You ready for challenge number 2?
Challenge number 2!
I've got another ball.
Okay.
With something else written on it.
Wait. Are you coming back?
Nope.
Huh. But I can't even see you from here. Like how am I? Huh.
You're gonna have to manipulate the light.
I have to see around a corner? I have to see around a corner. All right. I'll think of something. So you remember the tennis balls in the wall, right? Right? Okay, so the tennis balls are photons, what light is made out of, and the wall is a mirror. Now, right now, the photons are hitting the mirror and bouncing directly back. But what happens if they come in at an angle? Like this. Aha! Those photons are reflecting off the mirror and going that way, which means if I want to see what's emitting those photons, I can see it from here. The same thing happens when you look in a mirror. Oh, okay, mirror. Whoa. The mirror reflects the photons over here. I can see the tennis ball launcher in the mirror, which means if there was a barrier, between me and the tennis ball launcher, I can still use a mirror, and the photons would reflect off the mirror and it comes straight to me, which is how you can use a mirror to see around a corner. In fact, periscopes work the same way. Let's make a periscope right now. Hey, it's dark in here. Oh, right, because I'm gonna show you my laser. So the light from my laser bounces off this mirror
in a straight line. Haha, reflection. We can use the power of reflection to make the light go where we want it to. We're gonna build a periscope. Submarines use periscopes because it's hard to see when you're underwater. A submarine will extend a periscope up above the water. The image up here gets transmitted down here. So someone looking through the periscope underwater can see what's going on up on the surface. And here's what you need to build it. 2 cartons of milk, 2 small hand mirrors, scissors or a craft knife, a pencil, and science tape, which is the same as regular tape, except you use it for science. And remember, if I go too fast, you can always find these instructions on our website. Step 1, cut the tops off your milk cartons. Take your mirror and trace out a rectangle as wide as the mirror, then cut it out. Put some science tape on your mirror and stick it in the carton at an angle. Then put a piece of tape on the inside. Then get the other milk carton and do the same thing. Put a mirror on the inside and then stack the milk cartons together. But don't stack them with the holes on the same side. Make sure you stack them with the holes on opposite sides. And here is what's going on inside. You've got your 2 mirrors, and one is angled like that, and the other one is angled like this. Light from what you're looking at comes in, hits that first mirror, goes down to that second mirror, and goes to your eye. You can use it to spy on people from below the table. Or from around corners. So there you go, your very own periscope using light reflection. Did you know that your TV remote can be a flashlight? It's true. If you have the kind of TV remote with a little bulb on the end of it, then when you press the buttons, the bulb lights up. Yeah, I know what you're thinking. You're thinking, Phil, wait a minute, the bulb did not light up, and I've never seen the bulb on my TV remote light up when I press the buttons. Well, that's because your TV remote works on infrared, which is a kind of light you can't see, but you might be able to see it with a camera. If you have a digital camera or a camera on your phone, now you can see, It lights up. And because infrared light works the same way as visible light, in that it will bounce off a mirror, here's an experiment you can do at home. Bounce the light off your TV remote off a mirror and turn on and off your television. Check this out. You get a mirror, set it up just right, and then aim the remote at the mirror, and it turns off the television. Pretty cool, right? But now, let's max it out. I've got a complex series of mirrors set up here, and I'm gonna bounce the light from the remote all over the room. And here's what that pattern looks like. The light from the remote hits this mirror, which reflects to this mirror, which reflects to this mirror, and then this mirror, and then this mirror, and then finally to the television. Isn't that cool? There you go. Maxed out remote light bouncing infrared flashlight. I gotta come up with a better name, but still, it's pretty cool. Oh, right. Turn off the television when you leave the room. I solved Anne's first light challenge, seeing something far away, with a lens. It says 71! But now she's moved the ball around a corner, and now I have the solution. Mirror! A mirror will let me see around the corner.
Clever.
Right? Okay, so all I gotta do is put the mirror in a position sort of like that, I guess, and then I'm gonna sit in the chair. If you could help me adjust that mirror. Keep going that way. Keep going, keep going. Yeah, stop. Nice, okay. Go ahead and flip the ball around and I will read the message. It is too small. I can't, okay, I've solved this problem though. Okay, flip it around. The lens, I need the lens. So we'll use a mirror and the lens to, good. Yeah, okay. I'm gonna sit in the chair. You're in the chair. It is backwards. Oh yeah, a mirror inverts the image, doesn't it? Mm-hmm. That's okay, I can solve this.
All I need, whoa! Other mirror is all I need to solve this problem. So if I take this mirror and I put it here, let's see, there it is. It says 42.
Nicely done.
I
Nicely
am
done.
ready for anything. What do you got planned for the hardest challenge?
Are you sure you're ready for this?
Totally.
Challenge number 3.
Challenge number 3 starts now.
What? Wait. No. This is a light challenge. How am I supposed to do a light challenge if it's dark?
You have to get creative.
But it's dark. Okay, no problem. I will think of something. I will be back.
Okay.
Okay, careful.
I'll be waiting. Careful.
So you already know about reflection, right? That's when the beam of light, say from my laser, reflects off this mirror and bounces in a straight line. But check this out. If I don't use the mirror and I shine the laser against the underside of the water, it also reflects, just like a mirror. This is called internal reflection. If I have a stream of water and I put my laser beam into the stream, you can see that the laser bounces around inside the stream of water. It's being internally reflected, and the laser isn't going straight anymore. It's following the stream of water down where the water goes. Internal reflection. Now I know what you're thinking. You're thinking, Phil, how does this affect me in my everyday life? Internal reflection. Who cares? Well, I can tell you why you should care in 2 words. Fiber optic wires. 3 words, fiber optic wires. You see, fiber optics carry information all over the planet. The internet, maybe even your television, travels through fiber optic wires. The good thing is, because of internal reflection, you can bend fiber optic wires any which way or around corners, and the beams of light continue to go straight down inside the wires and get out the other end, making it go where you want it to go. Internal reflection, science.
Back to our light challenge. I've seen something small from far away, seen around corners, but now Anne has turned off the lights. But I have a solution.
Anne? Anne?
Careful.
Okay. Sorry, I forgot how dark it was in here. Okay, I figured it out.
Okay.
I have a flashlight.
No.
So all I need to do...
No. Hold on.
What?
There's one more rule I didn't tell you.
What's the rule?
You can't use visible light.
How in the world am I gonna do this if I can't use visible light?
It's a challenge.
Wait a minute. Okay, here, hold my flashlight for a second. I'm gonna make a phone call.
Okay.
I think I know what to do. I'll be back.
Okay.
I'll be back.
Oh, careful. Oh.
Oh, hey, good to see you. Speaking of seeing things, let's talk about the rainbow. All the colors of the spectrum organized in a beautiful pattern. But what are the different colors? I mean, what makes them different? Well, it all has to do with the electromagnetic spectrum. This is visible light. All the colors of the rainbow. And take a look at that little black line that goes up and down there. That's the frequency of the light. Light is a wave. You see the wavelength is a little wider out here on the red side, and it's a little closer together here on the violet side? That's because every color of light has a different length of wave or wavelength. And that is what makes them different when we look at them. But if you think that's all there is to the electromagnetic spectrum, then you're mistaken. So what happens over here on the red side? Does it keep going? Yeah, it does. What? Look, we got infrared here, and then we got microwaves. These are the same kind of waves you use in your oven. And then we got radio waves, which are the same kind of waves you use in your radio. They're all part of the same thing as visible light, huh? Let's take a look at the other end. Remember these short wavelengths over here beside violet? Well, does that keep going? Yeah, if they keep getting shorter, you get ultraviolet, and then X-rays, and then gamma rays. Huh? Pretty amazing. And look, it's all connected. From radio waves to gamma rays to visible light in between, it's all frequencies of electromagnetic radiation. How is it staying up? So everything outside of the visible spectrum is invisible, right? Wrong! Ha-ha! Bam! Huh? That is an X-ray, a picture we can take using this part of the spectrum. We can use special cameras to see outside of the visible spectrum. Huh? Huh? Right? Yeah. Okay, you got it. Huh? And look at these. These are night vision goggles. They help you see in the dark. They use part of the spectrum called infrared. For those of you keeping score, that's this part of the spectrum right here. Pretty neat, right? I would sell you these, but they're already spoken for. Oh, and here he comes now. Hey, Sal. Hey, how you doing?
You got those goggles I ordered?
Yeah, go ahead, help yourself.
Thanks for putting them aside. Can I put them on my tab?
Yeah, no problem.
All right, thanks, Sal.
Okay, see you later. Nice kid. He's always in a rush, though.
Phil? Is that you?
Yeah.
Do you need the flashlight?
I don't. Turn it off. I can totally make my way over to you. Oh.
I can hear you.
Yeah, I'm right here.
Oh.
Right here.
Hi.
Because I have night vision goggles. Ooh, check it out.
Oh, cool.
Pretty cool, right?
That's awesome.
So here's the spectrum again, and here's visible light. My night vision goggles use infrared, this part of the spectrum here with wavelengths just a little bit longer than the red we can see.
Outside of the visible light spectrum.
All right, I would say that's allowed.
No visible light, and I will see the next ball. Have you got it set up?
I set it up while you were out.
Okay, good. I'm gonna sit in the chair and see if I can see it. Okay, here we go. Oh wow, I can totally see everything.
Can you tell me what the ball says?
It says you win.
Nicely done.
So let's recap. This challenge is the same as the last challenge. The light from the ball was magnified by the lens, sent around a corner by reflecting it off a mirror, and flipped back around by using another mirror. But this time it's dark. So, using infrared light, thanks to my night vision goggles, I was able to see the ball and win the game.
The light manipulation challenge is done. Science Max experiments at large. Time to turn the lights back on.
Yep, absolutely.
Huh.
What did you do back there?
I guess we blew a fuse or something.
Uh-oh.
Science Max! Today on Science Max, it's all about gas pressure. Low pressure, high pressure, good ideas,
A nucleation fountain.
and bad ones. Let's carbonate pickle juice. All on this episode of Science Max, Experiments at Large. Greetings, Science Maximites. Today we're using fizzy drinks in our experiments. And a fizzy drink is just water with bubbles of carbon dioxide gas dissolved in it. So I thought since we exhale carbon dioxide, I could make a fizzy drink by just blowing bubbles in this water. Doesn't seem to be working though, does it? I don't see any bubbles, do you? No. Water does absorb carbon dioxide gas, but I don't have a fizzy drink. Weird. Time to check the book of science. Oh, in order to make bubbles, you have to have pressure. So... This is an air compressor. It takes air and compresses it, puts it under pressure. So... The container needs to be pressurized. Okay. When you get a container of a fizzy drink, the carbon dioxide gas is put in there under pressure, and it stays in there under pressure until you release it. That's the sound of the pressure being released. And when it is released, the carbon dioxide gas starts to expand. And when it expands, it creates bubbles. And that's what makes your fizzy drink. This process takes a while to run out, but eventually it will become flat. No more bubbles. But what if there was a way to release all of that carbonation all in one go? Well, there is. And for this experiment, all you need is your favorite brand of fizzy drink, Science Max brand Diet Science Cola. 100% science, 0 calories. And your favorite candy, like these science experiments. All the minty flavor that comes from pure science. So, all you need to do is open this up, take one of these, and put it in here with an adult's permission because it can get kind of messy. Whoa! What's going on here is all of the carbonation that was in the bottle is now being released much more rapidly than it would have been before. Now, why does this happen? Well, if you look at a carbonated beverage, you'll see that the bubbles don't come from everywhere. They come from the inside of the glass, or in this case, a lot are coming from the straw. And that's because the carbon dioxide bubbles like to find a little imperfection, something to hold on to in order to expand and bubble out. And a candy, such as this, has a ton of little tiny microscopic imperfections. So when you drop it in, there's a lot more places for the bubbles to attach, and that makes the carbonation happen a lot quicker. But remember, this is not a chemical reaction. It all has to do with carbonation. So that's what we're gonna be looking at today. Air pressure, more pressure, less pressure, and of course, we're gonna be maxing out this experiment. All right, I just need an expert to help me max this out. Let's see, oh, Cynthia from the Ontario Science Center. She'd be perfect for this. All right, good. Okay, come on, let's go. And, yep, that's good. Oh, hey, Cynthia!
Hey, Phil, how's it
Cynthia
going?
from the Ontario Science Center, you're gonna help me max out the science experiments and Diet Science Cola experiment. I think we need a better name for this.
Okay, well, we have the mints that have tiny little pores called nucleation sites on them. The gas inside the cola is gonna go through these nucleation sites, create a giant fountain. So why don't we call it a nucleation fountain?
Ooh, nucleation fountain, I like that. It's accurate and it sounds awesome.
There we go.
Okay, so we wanna max it out. So how many should we put in?
Let's say 5 more nucleation sites.
More reaction. Ah. I tried adding more mints, but one at a time didn't work. It doesn't,
No.
it's not, the bubbles are pushing it back out again. There we go, there we go. And then, yeah, I think if we put them all in at the same time, it would work better. So we came up with a delivery mechanism to get all the mints in at the same time. A tube with a magnet holding the mints up, which we screw onto the top of the bottle. Pull the outside magnet to release, and... Oh, nice.
Oh, yeah.
Oh, yeah.
That's a good fountain.
That is
a good nucleation fountain.
Nucleation fountain worked very well.
There we go.
Cynthia and I decided to try some other ideas to max it out even more. We decided to do some
Experimentation.
experimentation.
Oh, that's a good one. Yep.
And see if Diet Cola was the best carbonated drink to use. We tried 4 different kinds: Diet Cola, regular cola, lemon lime soda, and club soda.
Really just
It's just carbonated water.
carbonated water.
3, 2, 1, go. Whoa.
Science cola!
Science Cola, but I think that it was close.
I think it was the release.
Let's watch the replay.
Okay.
Yep, Diet Science Cola went the highest. So the next step is...
Maybe if we want to max the size of the fountain, we have to make a narrower stream.
Ooh, so a smaller aperture opening will be higher pressure
That's what I'm thinking.
because it'll be forced at a smaller opening. What else can we do?
We can launch it.
We could launch, well, you mean like sideways?
Yeah.
Yeah, I love that idea. So we'll put it on wheels. We'll put it on wheels.
Okay.
And then we'll launch it sideways.
Okay.
We got a lot of things to do. Okay, let's get...
We need time. Let's do it.
Get to it. Okay, we'll go
Okay.
to the lab. I'll get a mop. Nothing like a fizzy glass of water. And now there are ways for you to carbonate water at home with something like this, the Science Max Carbonation Station. You have a bottle of compressed carbon dioxide gas that's hooked up. You take a bottle of tap water, attach it, and carbonate it. Voila! Carbonated water. But this is Science Max. Why just carbonate water? Let's carbonate everything! Let's carbonate pickle juice. It's actually amazing. Milk! It's like milk meets water, kind of very odd. Chocolate milk? Oh no, that's way better. Carbonated mustard. Carbonated tomato juice, carbonated hot sauce. No, wait, carbonated, that was the hot sauce. No. Carbonated clam chowder. Oh, there you go. Carbonation, not just for water anymore. It is definitely not for clam chowder. No, that's just a big bowl of no. Never again. Cynthia and I are maxing out a nucleation fountain.
Yes!
Oh,
That's a good fountain.
We're changing our design a bit to see if a smaller hole in the bottle cap will make for a higher pressure fountain, which will make it more maxed out. We have this large hole. We've got a medium-sized hole.
We have a very small hole
So we're gonna see large, medium, or small, which one is the best.
to max out our fountain.
Exactly. But the problem is that our old delivery mechanism won't work if we keep the cap on. So we needed to come up with a new delivery system. So we drilled holes in the mints and put them underneath the cap on a pipe cleaner. They hang at the top of the bottle until we pull the pipe cleaner, and then they fall in.
All right, are you ready?
Oh, I'm so excited. Which one do you predict will be the best? This will have a larger geyser.
I
These
think
ones
this
be
will
smaller.
look cooler
Yeah.
because it'll be big, but this one?
The smallest hole, I think, will go the highest.
Yeah, ready?
Three,
2, 1. Definitely the biggest.
There. Whoa, careful, careful. Whoa.
This one is almost like a spray.
It's not like a mist.
Yeah,
it's a mist of cola. They all kind of work a little differently. The interesting thing is this one lasts the longest.
Oh.
There we go. So, this was cool, but not the best.
This one's still going.
It's still
It's
going.
not over yet.
You gotta give it points for still going.
I think this fountain looked the best, though.
This one was pretty good. So, a small aperture, but maybe not the smallest aperture, would be the best. So because of the force coming out of here, I think that we could probably do something like putting it on wheels.
And shooting it like a rocket?
Yeah, let's see.
On wheels?
Or like a car.
Oh.
Yeah, we'll make a nucleation fountain car. The Nucleation 1!
It's our race car.
It's our race car. It's got fancy wheels that spin really well.
And we decided to go with the medium aperture. So it's fairly big, but not too small.
Yeah, all we need to do is unscrew that, put that in there, and then pull it out.
3, 2, 1. Oh, good. Let it go. Oh, that's not so bad.
Whoa, yeah!
Missed the finish line.
Past the thing! Turn it around, turn it around!
Do you think we can make it get to the finish line?
It's
no.
spinning out.
Oh, wow.
Go! It worked pretty well, but there's always more ways to max it out. What if we just got like a giant container? Like, because we're using small containers, right? What if we just
So
got a
you
really
want
large
to carbonate
container?
a very large container.
Well, we'd have to figure out some way to, well, come on, let's go figure it out.
Okay, let's do it.
This is an egg. It's been hard-boiled and peeled, so there's no shell on it. This is a flask, and this is hot water. I pour the hot water into the flask, which means the air inside the flask starts to heat up. And when it heats up, it expands, and some escapes through the top of the bottle. I pour the water out, and then I cap the flask with the egg. Now this expanded air is starting to cool again, which means it's lower pressure, which means the higher pressure on the outside of the flask pushes the egg in. Ha-ha! Fun! And then, to get the egg out, Ah, I can reverse it. If I blow into the flask, I can increase the pressure inside. Ah, science! And now let's max it out. Max out container! Okay, pour out the water. Oh, careful, careful. And now, I put this water balloon on the top, and we'll just see what happens. The hot, expanded air inside the container is cooling and reducing in pressure, which means the higher pressure outside the container, it's happening, pushes the balloon in. It's happening! Oh. Success! Maxed out! Did you know that we live on the bottom of an ocean of air? It's called the atmosphere. And compared to the Earth, it's really thin. I mean, it's about as thin as this. Huh? Huh? Look at that. Not very thick at all. But it's a good thing the atmosphere is around, and not just for breathing. Though I am a fan of breathing. What do we want? Breathing! When do we want it? All the time. But did you know the atmosphere has different layers? It's true. I will walk you through them. No, I mean, come on, you gotta come with me. I'm walking over to walk you through them. Okay, the troposphere. This is the layer where we are all existing right now, where all of our weather happens. There's a lot of air molecules in this layer. Think of these balloons as air molecules. There's a lot of air in this layer. Yay, air! Next layer, the stratosphere. There's less air molecules in this layer, and it's where jets fly. Next layer, the mesosphere. There's even fewer air molecules in here, and it's where meteors burn up and turn into shooting stars. Fire, 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 fire! The thermosphere. Not many air molecules left up here, and this is where the northern lights, the auroras, happen. Woo! Northern lights. And finally, the exosphere. This is as high as the atmosphere goes. This is where satellites orbit, and if you see any air molecules up here, they're just passing through. Hello. And after that, nothing but the vacuum of space. Ooh, the vacuum of space. Of course, you know it's not that kind of vacuum, right? Right. Vacuum just means no air. There you go. The atmosphere. The only thing separating us from the vacuum of space. Roberta, your space vacuum got broken. I don't know how. Cynthia and I are maxing out the nucleation fountain.
Whoa. This one is almost like a spray.
It's not like a mist.
Yeah,
it's a mist of cola. Just to experiment, we tried using a giant bottle and pouring the Diet Cola in. I'm a little concerned about the science, but it didn't work.
Well, that's not very exciting.
Okay, so that didn't work at all.
No.
This is not a chemical reaction.
It's a physical change.
So it's the carbonation that matters.
Exactly.
When we poured the cola into the bottle, we lost almost all the carbonation.
How are we gonna max it out?
That's the question. So if we can't make a larger container,
more bottles?
We just have more bottles. So we'll just get a lot of them and we'll set them off in a sequence or something.
Okay, let's do a pattern or something. We'll max out the
I know
fountain.
what we should do. You know, we should do sort of like a cascade and we'll get a lazy Susaner or... This is a vacuum chamber. It's an airtight container, and I put a hose on it, and the hose is attached to a pump. Now, the pump takes the air out of the chamber, creating a vacuum. So, let's have some fun putting things in a vacuum chamber. Marshmallows in a vacuum chamber. The marshmallows grow larger, whoa, then shrink much smaller when returned to normal pressure. Why? Well, take a look at what happens with this balloon. The vacuum takes the air and the pressure out of the container, which was pushing against the sides of the balloon. Without that outside pressure, the air molecules inside the balloon can expand. So let's max it out with maxed out marshmallow. Just like the balloon, the marshmallows expand. But unlike the balloon, the air in the marshmallows escapes, so they shrink when the pressure is added back in.
They're almost the size of regular marshmallows.
It's the air inside a marshmallow that makes it fluffy.
It's not very fluffy.
The same expanding process happens with marshmallow cookies.
The marshmallow has completely deflated and it's all kind of hollow inside.
The frosting on a cake.
More cake! No, no! Oh! Look at this giant birthday cake. I can't wait to eat it. No! No! Why birthday cake?
And even shaving cream.
No! Shaving slime.
Cynthia and I have done a whole bunch of different experiments to find out how to max out the nucleation fountain.
So we'll just get a lot of them and we'll set them off in a sequence or something.
Okay, let's do a pattern or something.
Now we have a bunch of bottles and we're ready to try the maxed out version.
We've got our release mechanism.
With our medium aperture.
Yep, and we're gonna put the mints in all of the bottles and then we're gonna release them in a very coordinated,
Pattern.
rehearsed pattern.
Very rehearsed.
We've rehearsed it a couple times. We'll see how it goes. And we've got this lazy Susan, which will spin around and we'll see how it goes. And 3,
2, 1. 1,
2,
3,
4,
5,
6,
7. Surprise! 1, 2, oh, go, 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 3, 4. We did it!
Whoa!
It's raining Diet Science Cola. We maxed it out!
Maxed out! Nucleation fountain. That is as good as it's gonna get.
So let's recap. Our nucleation fountain is all about releasing the carbonation in our Diet Cola faster than normal. This happens because there's lots of tiny bumps on the mints for the carbon dioxide to grab onto and make bubbles.
High fives. There you go. Science Max, experiments at large, nucleation fountain. Excellent job. Now all we need to do is clean it up.
Clean up, and I think I need a shower with water.
Yeah, I think I need at least the towel.
Yeah,
But it's supposed to volumize your hair.
Is it good for
I
your
think
hair?
so.
I
Yeah,
hope so.
better than
'cause-
honey and things like that.
Science Max! Put on your helmets for this episode of Science Max. We try to build a human-sized cart powered by inertia, plus Newton's laws from a caveman to crockery. Inertia on Science Max, experiments at large.
Greetings, race fans and science maximites. I am Phil McCordick, and this is Science Max, Experiments at Large. Today, we're going to be experimenting with the drag racer. Huh? Pretty cool. It works like this. You pull the string and get the wheels going really fast, and then you let it go, and it just drives away on its own. The interesting thing is that I don't have to push it, it goes by itself. It all has to do with Newton's first law of motion, which is an object at rest tends to stay at rest, and an object in motion tends to stay in motion. Yeah. Let's get building. Here is everything you need to build your very own dragster. You need some popsicle sticks, some straws, and some shish kebab skewers. I love these. You can get these at the grocery store. Let's see, some elastics, and of course you want wheels, and I just cut my wheels out of cardboard.
So here's a quick explanation of how to build your dragster. First, use anything round to trace 3 circles out on your piece of cardboard. Remember, you want 2 big and 1 small circle. Then cut out your wheels. Then it's time to make the frame of the dragster using popsicle sticks and elastics. Just put 2 popsicle sticks together, then wrap the elastic band around them to keep them together. First you build one side, then the other side. Then add some pieces across the middle to give it support. Remember not to put any popsicle sticks too near the ends because they'll get in the way of your wheels. Next, cut the straws into small pieces and use an elastic band to tie them to the ends of the popsicle sticks. Then it's just a matter of sticking the shish kebab skewer in a wheel, passing it through the straws, and sticking on the other wheel. Don't forget that the small wheel goes in the middle at the front. You can trim the skewers afterward by just breaking it off short.
If you want step-by-step directions on exactly how to do this, you can go to our website. It's all right there. Now, the last part is wrap some string around the back axle so you can pull and the wheels will spin. Let's check it out and see how it works. Didn't work that well, did it? That's because we haven't added the secret ingredient. Plasticine, the perfect secret ingredient for all of your dragster needs. And also sculpting, because that's what it's for. Remember how I said an object at rest tends to stay at rest, and an object in motion tends to stay in motion? Well, the heavier something is, the more force you need to change its direction, either get it moving or make it stop. That is called inertia. It's the tendency for an object to resist a change in motion, either getting it going or making it stop. So, the heavier we make the wheels of our dragster, the more they will resist a change in motion. So what I've done is I've stretched out my plasticine, and then you roll the wheels of the dragster around in the plasticine, and this will make each wheel way heavier than just the cardboard by itself. And it will make it much better in terms of keeping the dragster going, because if the wheel has more weight, it will have more inertia. Now, I have to wrap the string around the back axle, just like that, and there we go. All right, let's try it out. All right, let's give it a shot and see how it works. Pull on the string, get the wheels going real fast, and there it goes. Now, of course, this is Science Max Experiments at Large, and we are going to do it again, and we're going to do it much, much bigger. That's why I'm going to the Center for Skills Development and Training. I thought it was bigger. Oh, right. Hey, Chris.
Hey, Phil.
How you doing? Chris is from Logix Academy, and he is going to help me max out our dragster. Now, you guys at Logix Academy go into schools and build all kinds of cool stuff with the students, right?
That's absolutely right. This is our dragster over here, actually. And this one has an electric motor, which is kind of fun. And these gears touch.
Ooh.
Wheels get going.
I like that.
And...
Oh, all right. See, our dragster works on good old human power. You pull the string, and there it goes. Now, you have a physics degree, right?
I do.
Which means you know Newton's first law of motion.
Of course, an object at rest tends to stay at rest.
And an object in motion tends to stay in motion. I thought it was gonna come from over there. Yeah, come on. All right, Chris, I want to make a dragster big enough that we can ride.
Whoa, okay. Well, it's gonna have to be pretty big.
Yeah, I think we have enough wood, though, right?
Yeah,
And oh, look, I've got some wheels.
Perfect.
These are bike tires, and I filled them full of air, so they're bouncy. Check
Excellent.
it out. Whoa, it's okay.
So, yeah, we build our frame out of wood,
Yeah.
attach the tires on, and then find a way to get them spinning.
And if the tires are spinning,
Yeah.
we don't actually have to push the cart because it'll just go on its own?
That's the idea. The inertia should carry, in the wheels, should carry us down the track.
So in this case, the object in motion is the wheels.
That's right.
And it wants to stay in motion, which means that when it hits the ground, it'll push the cart.
And hopefully us too.
And hopefully us too. All right, let's get building.
Let's do it.
So Chris and I get to work building the dragster. Our maxed out version is gonna look just like the popsicle stick version. A triangular frame with 2 large wheels at the back and a small one at the front. What's more, we're gonna do the same thing to get the wheels spinning. We're gonna attach a rope and give it a pull. When we drop it down, the inertia of the wheels should make the dragster take off.
All right, here we have our dragster. This is nice, Chris.
Yeah, it looks good.
So the only thing I don't understand is what are these for?
Right, so these are gonna help us lift the wheels off the ground like this.
Oh, okay.
Pull it back, and what's gonna happen is we're gonna run real fast with that string, and we're gonna give it a little kick, and hopefully it'll take off.
Ah, all right, I like it. So I just run backwards as fast as I can.
Fast as you can.
All right, here we go. Ready?
Yep, ready.
Okay, safety glasses on. And, oh, wait, did you want to sit on it, or?
Oh, right. Let's wait until we see it working, and then we can...
Okay, dry run.
Okay, dry run.
Ready?
Go! Run, Phil.
And go! Yeah!
So here's what happened. Remember, the cart has no power of its own. It was able to drive away from a stop using the inertia it got from its spinning wheels, and a little bit from Chris's kick.
That worked pretty well.
That was awesome.
Yeah.
I think we can make it go even better.
You think so?
I just think we need a bit more speed.
Yeah. All right, well, let's pull it back to the start.
Okay.
So what, the wheels weren't going fast enough?
Yeah, I think so. I think that you running, was great, but maybe if we use something motorized.
Well, I think using a motor feels like cheating.
No, not on the wheels. Maybe,
Oh, just to get the wheels spinning fast?
Yes, that's right.
But I don't know how that would work.
Well, I was thinking a power drill.
A power drill?
Yeah.
I don't get it.
Okay.
How do we use a drill?
Let me explain. So we'll take a drill.
Right.
And we'll attach it right under this axle here. And that'll get the wheel spinning a lot faster than we had it before.
Oh, I see. So you put the drill right here at the end, and it'll spin the wheel.
That's right.
Huh.
That's the idea anyway. And once we get it up to speed, hopefully a lot faster than before, give it a kick, it should go a lot farther.
Okay, great. So that's way better than me running all the way back with the rope.
I think so.
All right. Now here's the real question. Should we just go for it and have someone ride it when we do it with the drill?
Well, who gets to ride it?
Oh, rock, paper, scissors. Okay.
Let's go.
1, 2, 3. Oh,
yes.
All right. I will get a drill.
Okay.
What kind of bit do we need?
Hex bit.
Here's a fun experiment you can try. If you have something heavy, like this glass of water, and you put it on a piece of paper, you can experiment with inertia. If you move the paper slowly, the glass moves with the paper, because the friction between the paper and the glass is enough to overcome the inertia of the glass. But if you move the paper quickly, the friction is not enough to overcome the inertia, and the glass stays put. And now, let's max it out. Okay, let's do it. All right, now you might be tempted to try this at home, and you can, but please, for me, promise that you'll let an adult know you're about to do this. And don't use breakable plates. Use plastic plates, because this will take a couple times of practicing before you get it right. Put something on the plastic plates, because the heavier they are, the better it will work. All right. Did I mention not to do this at home unless an adult knows you're doing it? I cannot stress that enough. Okay, deal? All right, deal. Here we go. And there you go. Newton's first law. Thank you.
Our dragster worked pretty well, but now we're gonna try sitting on it and seeing if the inertia of the wheels is enough to accelerate the dragster and the human rider. Because we're gonna need a lot more inertia, we're gonna make the wheels spin even faster using a drill.
All right, power tools! Yeah, power tools! Woo-hoo-hoo-hoo! Yeah! Sorry.
When I attach the drill to the wheel, it works really well.
Yeah, that is really gonna work. All right, let's do it for real. So, what do you want? Helmet or blast shield?
Blast shield.
Blast shield. All right, there you go. You ready?
Go. There you go. Whoa, man.
Okay.
Remember, the faster the wheels are spinning, the more inertia they will have.
Ready? Ready. And... Well,
What happened?
So you went a foot. 1 foot. So why didn't that work nearly as well as the last time we did it?
Well, I think my extra weight caused a bit of the problem.
Yeah.
So the inertia wasn't able to carry us forward.
But the whole point of this is so that someone can ride the dragster, because why build it if we can't ride it?
That's exactly right. I think if we're gonna have someone ride it, we need heavier wheels.
Well, on the small one, we use plasticine.
Yeah.
I don't know if that's what we should use.
What if we used car tires?
Car tires. Oh, what, on this?
No, I think we're gonna have to build something bigger.
So so we build a whole new frame.
Yep.
What if we got like the axle of, like the back axle of a car or something?
That's a great idea.
The back axle of a car, and then what, we use the drill?
I don't think the drill's gonna be enough.
To move the, why? You don't think it's gonna be enough to move the back axle of a car?
Yeah, it's too big.
So what do we do?
Well, what's good at moving the back axle of a car?
Well, I mean a car, but we would have to take it off the car, so.
We could use another car.
We could use another, we could use another car.
You could use another car.
You'll have to explain how that works.
Okay.
Let's go get the stuff, and you can tell me how we're gonna use. So how do we use another car to make the first car go?
Okay, I'm thinking we jack one car up,
yeah,
back our big dragster.
Newton's laws in 60 seconds. Isaac Newton was a super genius, and among the many things he did was come up with 3 laws of motion that describe how everything moves, or doesn't move. I will demonstrate using myself. Newton's first law, an object at rest tends to stay at rest. An object in motion tends to stay in motion. Newton's third law is for every action, there is an equal and opposite reaction. These sandbags weigh as much as I do. So when I push them forward, I go backward the same distance. Now, Newton's second law is F equals ma. Force equals mass times acceleration. How hard you push something is equal to its mass, or its weight, times its acceleration, or how much you change its speed. I know, that one's a little bit more complicated, so we're gonna have a whole other segment describing that one coming up. Meantime, let's recap. Newton's first law, object at rest tends to stay at rest, object in motion tends to stay in motion. Newton's third law, for every action there's an equal and opposite reaction. Newton's second, Newton's 3 laws of motion. Now how do I get down? How do I get, oh wait, I know. Oh no, that was not a good idea. That was...
Now it's time for Science So Simple, a caveman could do it. This is a caveman. This is a door. It is a well-known scientific fact that cavemen do not know how to open doors. This is Newton's second law. Force equals mass times acceleration. Our caveman thinks he can open the door if he uses force. Well, what if he was to walk briskly into the door? Then the force that he will hit the door with will be equal to his mass, or how much he weighs, times his acceleration, which will be walking speed to 0. It didn't work, did it? No. Looks like we need more force. If we want to increase the force, we need to increase the mass, increase the acceleration, or both. A rock! That's perfect. If the caveman holds the rock, he has a greater mass. Now we just need to increase the acceleration, which means going faster. Let's try running. Go on. A little further. That's good. Now the caveman is going to run at the door. To get more force, we've increased the mass to a caveman plus a rock. And we've increased the acceleration to go from running speed to 0. And there you have it. That's how Newton's second law works. Join us next time for how doorknobs work.
What?
Our inertia-powered dragster just wasn't maxed out enough. So Chris and I built a second dragster, the Dragster Mark II. This one is a welded metal frame, and instead of bike tires, we're using car tires because they're much heavier than bike tires. And to get the tires spinning fast enough, we're going to use a car. That's right. We jack up an actual car and have the tires touch each other. Then we can get those heavy tires spinning fast enough to get enough inertia to get me going from nothing. The Science Max build team pulled out all the stops on this one. Just like the smaller version, the dragster has to be up on jacks so the wheels don't touch the ground as they get spun up. The wheels of the dragster touch the wheels of this working car, which is also jacked up. That's how we're gonna get them spinning fast enough.
Chris is over there. He's got a rope, just like I'm gonna have a rope. And when we're ready, we're going to run forward and pull it off the jacks, and our dragster will go. We hope, right? That's the plan, right?
Yep.
All right.
I think it's gonna work.
I think we should do it. Ready, Chris?
Ready.
You ready, Paul?
Ready.
Fire it up. Go, go, go. Faster, faster, faster. Faster, faster.
Keep going.
All right, Chris. After 3, right? 1, 2, 3, go. Nice.
It's pretty good.
Yeah, that worked. All right, are we ready for me to be in it?
I think so.
All right, we're gonna do it. The helmet's in the Max van. Do you have the keys for the Max van? Keys for the Max van. Here's another small experiment you can do with inertia. Take a stack of checkers, or game pieces like I have here. Oh, or coins. Coins work really well. And a ruler, or something else that's flat. This is the kind of stick they give you at the hardware store to stir your paint with. Now, you can knock checkers out of the middle of the stack without the stack falling over, if you're very careful. You see, the friction of the checkers leaving the middle of the stack won't be enough to overcome the inertia of the rest of the checkers. Ready? Now, let's max it out. Oh, I have these pizza boxes, and they should work the same way. You see, you get a stack, and don't worry, I've already eaten all the pizza. And I put them on there like that, and now I need a ruler. And what I've got is this cricket bat. You see, it's got a nice flat edge, just like the ruler. Now, if this works right, I can hit it hard enough to knock out just 1 or 2 pizza boxes, and the rest of the stack should stay. Here we go, ready? Science! Awesome. And there you have it, Newton's first law. An object at rest tends to stay at rest, and an object in motion tends to stay in motion. An object in motion tends to stay in motion. Usually there's a sign that kind of...
Well, our inertia-powered dragster worked really well. And now it's time for the final step. Me, riding it to glory!
Now, I know it probably doesn't need saying, but don't try this at home. Not that I think you really can try this at home because this is kind of involved, but I figured I should probably tell you guys just in case you were tempted to try it at home. We know what we're doing. We know what we're doing, right, Chris?
Yes.
Yes, yes, we know what we're doing. All right.
Fire it up. Keep it going. Keep it going. All the way. Whoa. All the way. 3, 2, 1, go! Woo!
Yeah! Yeah!
Woo! How's that for inertia?
Wow, look at that. That's amazing.
Cool.
High fives! Yeah!
Let's recap. The weight of the tires, as well as how fast they were going, provided enough inertia to accelerate me and the weight of the dragster. The objects in motion, the wheels, wanted to stay in motion so much they moved the dragster all by themselves. Inertia, and Newton's first law of motion.
Thank you for joining us on Science Max. Let's go again. Your turn?
Yeah, my turn.
Okay. Woo.